Okay, we're going to start on instant centers of zero velocity now. So what we have here, the drawing's a little lacking, but here's a wheel, it's rolling, all right, and I have this leveled off. It shouldn't be as leveled off as it is. Uh, but picture as this rolls, this will come down into contact with the ground. As it continues to roll, it'll come to the top of the wheel and make its way back down to the road again and back up, so on and so forth. So this is the path of a point A on a wheel that is rolling without slipping. All right. These 2 points here, if you think about it, as this comes down, if it's not slipping, there's no motion along the, say, X or horizontal plane. All right. It's come down and it's about to start going back up. So it comes down and it stops. And then it goes up again. So here's the wheel is moving, but there is one point on the wheel that is physically stopped. All right? All motion is then, so if this is stopped at this instant, it says everything is rotating, because it's a rigid body, everything is rotating relative to this one fixed point. Okay? So, let's something to contemplate. We can actually use this to benefit us. But let's analyze this wheel a little more closely. So I have a point here, A, on the ground. And this wheel is rolling along like so. So it's going this way. We have omega, we have alpha. So angular velocity, angular acceleration. Now, if this thing were to roll, let's say a little while ago, this point here was down on the ground. And now this point A is on the ground. Well, how far has this wheel rolled? This path length, if this rolls without slipping, this arc length here will be the path length. Okay, if it's not rolling without slipping, if you get one roll of the wheel, the distance you'll travel forward would be the circumference, 2 pi r. All right, so what can we say about this? Well, the path of the center of the wheel is going to be r theta. Its speed will be r theta dot or r omega, just dealing with the magnitude here. Its acceleration will be r theta double dot or r alpha. Okay? So that describes what the center is doing, and it's all based on path length. Okay? So let's just put this, let's add that in here. Arc length equals path length. Okay, so we know what G is doing. Let's contemplate what's A doing. All right. Well, knowing what G is doing, bringing this up here, so we know G is moving minus r omega, that's the speed, and we go minus x, that creates the velocity of G. And so since this is a rigid body, A must rotate relative to G. Okay, so the velocity at A would simply be plus omega cross r. So omega is counterclockwise, so that would be omega z cross the distance down minus ry. It's right here. And so that, take the cross product, add them up, A's not moving. Well, we knew that from what we did above, when we looked above there. What's the acceleration of A? Well, once again, let's think about this intuitively. If this is rolling without slipping, this point comes into contact with the ground, it's not moving forward or backward. What's its next move going to be? Straight up. All right, so when we do this, it makes sense that there's no horizontal acceleration or tangential, but the normal acceleration will be straight up. That's its next motion. So if we go look at acceleration of A, AG, well, is minus r alpha. All right. This has no normal acceleration. What does G do? G just purely moves in the horizontal. So this was based on path length. So ag minus r alpha x, there's the acceleration of g. And then we just we need to go from g to a. So a rotates relative to g, so you'll have alpha z, alpha was counterclockwise, cross r, which is minus ry, so length r down. And then we have plus omega squared ry. So normally you would say minus this direction down, but that would just flip you back up again. So let's just get that plus sign in there. Add it all up. You have the normal acceleration pointing right back up at g, omega squared r. Okay? Now, we'll notice that normally when you see this term, this would be like so. All right, this is a distance r in the minus y direction. So that flips those two signs, makes that positive. So here's what we have. A instantaneously has zero velocity, but it definitely has acceleration, and it's going up. All right. Another problem with instant centers. And so suppose we were asked, find the instant center of rotation for the following system. So what do I have? I got a wheel, and so it's rotating. We have omega, you can see going like so. And so here's v. It's we have basically this wheel is rotating in between two belts. So the top belt is going along at velocity v. The bottom belt is going here to the right at velocity 2v. It's going faster. Now it stands to reason if this was v and this was v, that this thing would just be in the center. That would be its instant center. It would just be rotating about its normal geometric center. All right. So let's look at this thing here. We've got no slip again, but we have v here and 2v there. So let's think about this, how we're going to attack it. And so here's just a little picture of what we have. So if this is rotating about something, let's think about that. When you have rotation, velocity is tangential to the rotation. So that means the center must be perpendicular. If this is tangent, then the center's got to be perpendicular to that. So somewhere along this line, and we get by the same argument this one, this is tangential, and somewhere along this line, the center's got to be here. I don't know where, but I know it's along here. So I know this distance here is 2r, so I'll call, to the one center, I'll call it x, and the other one 2r minus x. That's just straight algebra. Well, we know, so then what can we say? This velocity divided by this radius, if we take it to the center, that would be, you can kind of do it this way. That's where the omega would be based. So, and when we think about it, there's only one angular velocity. So therefore, this velocity divided by this radial distance to the center, which we don't know, but we'll find out, must equal this velocity divided by this radial distance to the center. That's what I have here. And that's an ugly omega. All right? Well, if we solve this equation, we wind up with x equals 4/3 r. And so we stick that back in here, and we get omega is 1.5 v over r, if we wanted to find that out. Now, one of the things you'll notice in these problems, instant centers only refers to velocity, okay? Only velocity, okay? We don't have this concept working for us for acceleration. All right. One last problem in this category. And we'll kind of show some of the tools and things we can do with an instant center. So let me get set up here. So what I have here, that's ugly. I have what's called a crank slider mechanism. Again, in a following course of dealing with mechanism design and kinematics, you'll see a lot of these things. So this is a crank. So the idea in this thing is this thing rotates around. So you'd have like a motor or something on this going all around. And then here's the follower off the crank, and that takes us to this slider. Okay. You could be having this driven as in a combustion engine, and here's the piston in the cylinder. Okay, so lots of variations on things like this. So this rotates around, and this just follows that and connects to the piston, so the piston will just be going bing, 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 like so. So for this problem, I have, I'm going to do instant centers, so I only care about velocities. So here I have the cranks at 45 degrees, and the angular velocity here at the crank is 10 radians per second, counterclockwise. You'll notice the little symbols here. These are connected to ground, so they're not moving. So velocity here is 0. And I've got pure rotation. Okay. Irrespective of instant centers, since if I'm rotating around this point, then omega times r, which is 1 meter, says A is moving at 10 meters per second perpendicular to that. We know that. We don't need any special math or anything to get there. We know that. All right. Then I have the follower is 2 meters to get to where the slider is. All right. Now let's take a look at B. So, let's look at AB. If I look at what AB is doing, all right, as this rotates like so, here's AB here, but as this rotates up, it's going to go like this. You see that? Now, that motion will change as it gets past the 90-degree point, but just in the next short while, as this rotates up to here, AB is going to do this action. You see that? So, it's not going to maintain this orientation. It's not going like this. It's going like that. So, AB is having complex motion. It's got a translating component, and you can see that right here, because what's this doing? It's just moving this point on this link at B. All that does is translate back and forth. But A is rotating relative to it. So we have translation, and we clearly have, when you look at the whole link, we have rotation. So it's a complex motion. All right. So what I want to do now is I just want to take a look at B. All right. So if I look at B, all right, A, what can A do relative to B? It can only rotate. From B's perspective, if you're sitting here, if you could be riding the slider, okay, this thing can only do this relative to you. That's all. That's the only options it has. Okay. Now, so at every other point, so here I have this link, and it's shown as a bar, but use your imagination a moment. Suppose I get a creative artistic streak. Rarely happens, but let's suppose it does. Right? So suppose I went and welded a great big piece of sheet metal onto this thing. And so it's this great big piece of sheet metal. And so as this moves, this whole sheet metal will be going and doing what it does. So if I looked at B here, there's this big piece of sheet metal. So look at A. What's A going to do? As A goes up, B is going to see A do this. It'll rotate clockwise relative to B. All right. So here's B. As this thing goes, B is going to be going this way. No question. The rest of this link from A to B is going to be rotating clockwise relative to it. So if we had a clockwise angular velocity, so let's see, clockwise is going like this. Okay, pictures going this way. So as you went further and further and further away from B, like let's say here I have this point C, B will have its velocity going in the negative x direction. No problem. But if I go far enough away, think what's going to happen. Because as this link rotates this way, it'll be omega times r, whatever that r is. Now a bigger r and a bigger r. And eventually I will get so far away from this B that I can find a point C where the velocity at this instant will be 0. I've got a velocity going to the left, but I've got rotation. As this thing turns, I've got rotation relative to this point. So all along this line, the velocity to the left is going down, 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 till this velocity here plus that velocity there equals 0. Okay? There will be that point. Guaranteed. Okay? So, let's ask just some questions about this. So, here we have what would be, if as we extend off along BC, what would be the direction of the velocity of C with respect to B? So, holding B still, what is BC? That sounds kind of funny. If you were sitting here, what would you be seeing on the rest of the link? From your perspective, all the velocity. If you're sitting here and just riding with this thing, and you had that sheet metal here, everything along here would be going this way. Okay, my pen points in the direction to the right. So then we looked at that. Given this clockwise rotation, is there a point along here where the velocity would be 0 at this instant? Absolutely. Okay. Next question. Bringing this up a little bit. If we're on a rigid body that's moving, how many points can have 0 velocity? Now think about this. Can you have 2 points if the overall system is moving? Can you have 2 separate points that aren't moving? And the answer is simply no. It's impossible. If you have a rigid body, how can, right now, let's let this, here, I'm going to let this rotate as well as I can about a fixed point right here. How can you have any other point rotating? It's impossible. Absolutely impossible. There can only be one point where the velocity is 0 if there is motion. Now, if my cell phone's sitting here, there are infinite number of points, depending on how much you want to break it down, that aren't moving. But once it starts to go, so I'll have it translate. There are no parts, as I translate, that have 0 velocity. But once I allow a rotation component in here, there will be one point somewhere in the universe that if I could attach sheet metal to this thing, that at any given instant, because of rotation, there will be one spot that doesn't move. Okay? Now, and in fact, we can look at it, I'm not going to complicate it any further, but just picture, here's a cell phone. It's rigid. If it's rotating, there can only be one spot that has 0 velocity. And if we look at this link right in here, this point's going to the left. It means everything's rotating clockwise relative to it on this link. If we go perpendicular to this translation, we will find one spot on this link that has 0 velocity. And that must be the instant center for the entire rigid body, because you can only have one spot, only one, where you have 0 velocity. You can't have 2 separate ones and still have motion. Once you have 2 points with 0 velocity in a rigid body, it means you're not moving at all. You are completely still. Okay? This is very important. So, if I found this point based on this, and if I knew what omega was, where this velocity was, it would mean this point would rotate here. A would rotate around there. So let's contemplate this some more. Okay? So here I have this. A is definitely moving in this direction at this instant. So if I'm sitting on A, what do I see B doing? Okay, we know that overall B is moving to the left, but just from A's perspective, if A thinks it's the center of the world and that's all it knows, okay, in its world, because as A goes up and it doesn't know it's moving, it thinks it's still. B relative to A is rotating this way, right? It's going to go that way. That's clockwise. Same as this goes clockwise relative to B, B goes clockwise relative to A. So what is that saying? All right, so I have clockwise rotation. So here I am here's 10 meters per second. All right. From this point, as I go along, if I take a line perpendicular to this 10 meters per second, just go out here, continue out, relative to going clockwise, it'll be minus 10 this way, plus omega times r that way, plus omega times r that way. R gets bigger and bigger, and there will come a point where we hit 0. So along this line must be the 0 point. But along this line must be the 0 point. Well, what this tells you is if you can find the tangential velocity vector on any 2 points, obviously this one's here, this is rotating like so this is right here, and on both links, the velocity of A relative to this link and that link, they're pinned, they have to be the same. So knowing this velocity direction, knowing that velocity direction, draw a perpendicular like so, draw a perpendicular like so, and you will find the point, if you could weld a piece of sheet metal on the body, where at this instant, and only this instant, the velocity is actually 0. So this was an unbelievably powerful tool in the days before computers relative to linkage design, because people could start drawing something, and so then using drawing tools, they could go boom, boom. Now I know what this is, the 0 point. Well, that's huge, because now I can say, oh, if that's 10 meters per second, and I can measure that on a piece of paper, I'd have 10 divided by r, bam, I know the omega. And once I know the 0 point, I could figure out the velocity in any other point on this link instantly. I could do this all graphically without having to do a bunch of mathematics. This was an extremely valuable tool if you're looking at doing position and velocity analysis. Unfortunately, it doesn't extrapolate out to acceleration, but historically, it's a very, very useful tool. So let's just finish the story relative to our crank slider mechanism that we're talking about. So relative to A on AB, here's A, where must the center of rotation be? Relative to A, well, here's the velocity, take it back perpendicular. So it's on a perpendicular line to VA or from VA. Our conclusion, since there can only be one angular velocity for the device, the instant center must be where the perpendiculars from VA and VB meet. Or you could look at it, since there can only be one spot that has 0 velocity on a rigid body if it's moving. Okay, and so this is what we talked about doing. So once you have this, you could construct this using drawing tools. AC would work out to be that. CB would be roughly 2.8 meters. And you know this is a 45, 45, 90 triangle, so that once you know this distance, that would determine where the piston is, so you can do some position analysis. As we said, knowing VA, dividing by this distance, AC, that tells you the angular velocity, and so going from here, we can go down to there. So VB would be the angular velocity times this CB length, and so there we get the velocity of B. of the piston. So here's our conclusion. We can use instant centers to graphically determine velocities anywhere.